They're not listening. Anyhow, see, they listen to you. You're not even using the microphone. Okay. All right. So our first talk after the break will be Andrew Collette, time-resolved temperature measurements in hypervelocity dust grain impacts.
Great, thank you. I'm talking about temperature measurements for dust grain impacts. So this thing here is the most dramatic photo I could find of an impact-produced light flash. This is actually from a millimeter scale projectile fired at the NASA Ames range into a target. And it just kind of illustrates the phenomenon that we're using to do diagnostics. So when you have a particle moving at very high speed relative to the sound speed in the material, you can actually get on impact, you can get a bright flash of light in the visible range. And that carries with it information about the quantities of inside the plasma or the gas produced in the impact. And one of the things we're looking at is the temperature. So just to give you some background here, I work at CCLS, the Colorado Center for Lunar Dust and Atmospheric Studies, an NLSI node focused on understanding properties of the moon. We have a flagship device that Tobin Munstad described to you this morning, the Dust Accelerator facility there. It's used for basic science investigation, in which this qualifies, and also for instrument calibration, and it is available for use by the community. So we're right now in the middle of a campaign of measurements trying to understand the various properties of the impact process. And so these are kind of the 5 areas I identify here that we have ongoing experiments to address. So impact-produced ionization. Mihai also showed you a time-of-flight spectrometer this morning. Cratering studies. We can take electron micrographs of the craters that are produced by high-speed impacts, generation of neutral gas by impact, ejecta, and then finally the thing that I'm addressing today, which is temperature measurement by the emitted light. So this is a summary / outline for my talk. So the main results here are looking at the impact-generated light flash of particles of a relatively wide velocity range, 1 to 40 kilometers a second, impacting a metallic target. Why a metal target? Well, first of all, it's easier, and second, than trying to make a real mineral surface. And secondly, it turns out from work in the 1970s that tungsten in particular has a very high efficiency for converting energy into light, kinetic energy into light. So we can measure conditions on the microsecond time scale following the impact. That means from 1 to about 20 or 30 microseconds. We are using a 3-color technique. We have 3 photomultiplier tubes with 3 narrowband interference filters looking at 3 wavelengths. And we reconstruct the blackbody temperature as a function of time. We can do this on a per particle basis, which means that we can do scaling experiments and look at how this changes with velocity, for example. Here are some of the findings that I'll be presenting today. This is time average temperatures, meaning characteristic for the whole length of the flash, in the range of about 2,000 to 5,000 degrees Kelvin. It increases with velocity. There are initial temperatures compared to this 20 microsecond time scale up to twice this amount. We also find that there is the power, the black body radiated power from the flash is constant over, to me, a surprisingly long amount of time. Photomultiplier traces that people have taken in the past peak and then show a very rapid fall off. And so if you reconstruct the entire black body history, black body curve of the event, it turns out that what's going on is that the peak of the emission is shifting into the infrared. And so actually the total power integrated over wavelengths is actually constant for quite a while. So there we go. So this is not the first experiment looking at light flash. There were a number of experiments undertaken in the 1960s and 70s, in particular with the Heidelberg facility. They have an accelerator over there. Most of the work was done, early work was done by Eichhorn. This is a plot from Eichhorn's paper in 1975. The axes here are light energy on the y-axis and velocity on the x-axis. And as you can see, the light energy produced in the impact is a strong function of velocity. You get an exponent in the order of 3 or 4. He also did some estimates of the blackbody temperatures and found things consistent with a few thousand degrees Kelvin. And so as far as the total conversion efficiency of the kinetic energy, 0.01 to 0.1% of the energy goes, of the total energy of the impactor goes into light emission. So if we want to measure a temperature, it would be nice if we could treat it as a black body. And it turns out that's not a bad approximation. There are the emission lines, for example, which are a little bit deviation from the ideal blackbody case that have been seen in impacts and light casting experiments. It's a little bit more difficult to perform in spectroscopy, although we're going to try on dust impacts because the quantities of light are so small. These are signals that you need photomultipliers tube to see. The total number of photons, I think, is on the order of 100,000 photons for the entire flash. So measurements by Eichhorn and also earlier measurements in this country were conducted and determined that blackbody radiation is a reasonable approximation. So this is one of Eichhorn's plots showing a bunch of different wavelengths. This is not per particle. This is an ensemble over many, many, many flashes at different wavelength bins, and it fits reasonably well to the blackbody curve. So Tobin Munsak gave a great overview of this machine earlier today, so I won't repeat too much about it. But the experimental device we're using here is a dust accelerator. So it fires micron and submicron grains into a target chamber. The full velocity range of the machine is in the order of 1 to 60 kilometers a second, demonstrated. We can characterize on a per particle basis the velocity and mass of each particle. We also can do active down selection to make sure that we only can study, if we, for example, want to study a narrow velocity range or a narrow mass range, we can select only particles that meet that criteria. So this is a schematic of my setup here. So I have incoming dust grains that strike a tungsten target, producing a light flash. Up to 4 photomultiplier tube modules can observe the flash. In the experiment, we're going to use 3, 450, 670, and 400. It has about a 1 microsecond or a half microsecond integration time, depending on the particular experiment that we're talking about. This is a plot of the raw output from one light flash. So the 3 traces here are light coming from each of these 3 photomultiplier tube modules, one at 400 nanometers, one at 450, and one at 670. You can see the characteristic time scale here for the light on each channel is about 20 or 30 microseconds until it goes away. This particle is 7 kilometers a second and about, I'm not sure what radius this is. I believe this is about 500 nanometer radius. So I won't go, make you read the entire slide here, but the idea is that we have these 3 traces versus time at 3 wavelengths. And so as a function of time, you can do a temperature fit. So we divide the time history up into time bins, into 1 microsecond or half microsecond time bins. And then for each bin, we have 3 values of photocurrent. And we have a model for how the 3 tubes respond to a blackbody of a certain temperature and area. And so we can actually find a temperature area pair that best reproduces the 3 photocurrent signals we observe. So we get temperature, and we also get the radiating area, which means we get the power. So here's the total ensemble of data I'll be talking about today. So this thing on the top here is the distribution of particles that form our data set. So this is velocity on the x-axis, it's log scale, and mass, also a log scale. So for various experimental reasons, most of the particles we got in this data set were below 10 kilometers a second. Light flash really starts kicking around 2, so it's we can actually see a light flash, but we do need some more particles up here. So one of the things we can do with this is to try and look at the scaling as a function of velocity. And so one way to do that is to define a certain temperature on a per particle basis. And so one way to do that is to say, let's take an average, time average temperature and look at how that scales. So in this plot on the bottom here, this is also velocity. The y-axis now is in temperature, in Kelvin. This is log scale, and this is linear scale. And so it does increase with velocity. What we notice is that it rolls over. It doesn't increase linearly. And so there's a saturation effect that comes in. I'm not sure whether that's due to just better radiation efficiency. That does go like T to the 4, so it's possible, or what. We would like to improve the quality of this and get some more particles and determine whether or not this actually fits the power law. Eichhorn found power law is describing the intensity and total energy, for example, that scale very nicely with V cubed or V to 3.5. So for time resolved measurements here, we have the 3 traces. We bin it into individual photocurrents. This is photocurrent versus time, and we have 3, a triplet for each time interval. When we do that, we can actually fit, as a function of time, the temperature. So this is temperature, this is effective radiating area. These are 2 parameters in my fit here. And so what you can see is that this dashed line here is that time average temperature that we got. And so at early times it deviates. It actually is quite higher, up to about 5,000 degrees, compared to the 3,500 degree time average temperatures. And the radiating area, you can see over here we have temperature, we have area. So in the next plot we can actually get power as a function of time. So each of these 3 plots here, the 3 different colors, color is a different particle, ranging from 3 kilometers a second to 7.3 kilometers a second. And we can actually compute, sigma, sigma b t to the 4 and get power. And so that's the thing over here. This is power versus time. And so what you can see here is that the power for each of these 3 particles actually remains elevated on the order of a microwatt for up until the fit becomes into the noise. You saw those traces went down into the noise at about 20 microseconds. And so what this is telling us, compare this to an unfiltered trace over here. So this is an unfiltered trace. This is a different particle than these 3, but you can see that this is kind of falling off rapidly on the same kind of time scale. And so if you reconstruct the entire blackbody curve, you can actually see that the total amount of energy, including the stuff in the infrared, the power is actually constant for quite a while. And so what this means is that if you want to look at the total light energy emission and the scaling of that as a function of time, as a function of velocity, you should really use the total integrated wavelength integrated signal instead of just the range that photomold card can see. So I'm almost out of time here, so I'm going to go ahead and put up my, if it'll let me. Can we have the next slide? Great. My summary slide. So just to summarize, impact-generated light flash is a diagnostic for temperature. We find temperatures in the range 2,000, 5,000 degrees Kelvin, increasing with velocity. I want to briefly mention future work. We've actually collected a lot of data just a few weeks ago, meaning many thousands of particles. We can fill in the gaps in that scaling plot and see whether or not there's actually a power law, for example, that describes it. And also, we've added an additional PMT module to improve the quality of the fit. And we also did a number of impacts on various target materials. The first one used tungsten because of its high light efficiency, and we also used a variety of materials in the last one that have different densities and sound speeds. So I'll take questions. Thank you.
Could you say anything about how a regolith, say a porous material, would affect the temperature?
It's a good question. And so this is kind of an idealized experiment. We're looking at you're firing on a metal that's easy to understand and easy to reproduce. I can tell you that the quantities that people expect to impact this kind of thing are the density and to a lesser extent the sound speed and melting point of the material. So to the extent that the regolith is made out of different materials than, for example, tungsten, there would be a difference. So I don't know the exact, I can't estimate, off the top of my head what that would be, but I imagine that it would make a difference. Right, and so porous materials. So the scale of the impact here is on the order, the craters that you form, for example, are by the order of a micron, and so it's more of, it strikes me as being more of a particle-on-particle thing as far as the light flash. How much of the light gets out, or what the angle that you see at it, would also vary quite a bit, because I imagine if you're firing into a porous material, then you'd be hitting the side of a grain or the front of the grain, and it would depend on which one you hit.
Yeah, just a question on have you taken into account the spectral emissivity of a tungsten? I know that's pretty low in the near infrared. So you have to make a temperature correction for that.
Yeah, sure. So so I mean, this is being treated as an ideal black body, and so there's no material dependent. I mean, you could say it's a gray body, and then you'd have